Today I will present on robots that suggest safe alternatives for my final risk deliverable. The motivation behind this work is that goal condition policies are useful because they allow robots to generalize to human preferences. However, they're not guaranteed to be safer to succeed when faced with out-of-distribution requests. Previous works focused on detecting uncertainty and stopping to ask for help, but they failed to be proactive in guaranteeing task succession or safety. In our work, we introduced an online closed-loop monitoring framework that incorporates both safety and task success constraints. Here, we introduce a value function network that encodes safety and liveness. We learned a policy condition time discount value network from Hamilton Jacobi Reachability that quantifies the safety and liveness of a given goal condition policy. This can be used as a safety monitor online to see if, given the initial state and goal, the robot can successfully execute a policy. We also introduced the notion of optimizing over alternatives. And we formalized this notion with a concept called control barrier function in goal space. And the intuition behind this idea is to find an alternative goal that is close to the original goal, but is also safe. And the safety constraint is encoded in the value network previously, and we can use this as a constraint for our optimization problem to solve for a close but safe goal. Since this is a nonlinear program in the goal variable, we have to solve this approximately through sampling. In this low-dimensional toy example, we have this robot trying to navigate through this narrow passage to reach the goal. The human proposes a goal, but the robot deems it unsafe, so it optimizes over alternatives and it finds a new goal that it can successfully reach without colliding with the wall. Here, for this high-dimensional manipulation example, we start with an initial state as 0. On the right, we see that the human proposes a red goal and the robot naively accepts, in which the policy leads to unsafe behaviors where the robot knocks over the bowl and also collides with the desk. In addition, if the human proposes the red mug, for instance, and the robot naively accepts, it will not be able to succeed the task because it fails to grasp the cup itself. And finally, on the right, when the human proposes the red mug, the robot optimizes over the goals and finds that the brown bowl is safe and will be able to successfully execute the task. And once the human accepts, then the robot can successfully carry out this policy, proving its succession and its safety. We compare our method to open loop monitors. So for this, our baseline is to train an ensemble of policies. And this can be any number of policies, but we use 5 in this case. And we find the mean and variance between this. And if the variance between the ensemble of policies is high, then we stop and ask for help from the human. In the top figure, we see that the policy is rolled out immediately, but we have to check for uncertainty at every single state. And uncertainty is actually detected while hovering the object itself. And the human has to intervene at this point because uncertainty is high. But when we actually roll out this policy further, we see that the robot is actually able to lift the object so that human intervention was actually unnecessary. In the bottom figure, for our approach, we check for success pre-execution, so we know beforehand if the task will succeed or not, and we do not have to constantly monitor the robot actions in real time. And the policy is ruled out successfully because we were able to check pre-execution, not constantly during execution itself. Key takeaways from this work is that policy network ensemble uncertainty is not necessarily correlated with safety violations, nor is it a reliable indicator of success rate. And closed-loop monitors that leverage HU reachability exhibit the highest true safety violation detection rate. Future work includes representing goals through LLM and VLM prompts and incorporating latent states in the value network. And finally, I just want to thank people in the intent lab, Ken, Robbie, for helping me tremendously with this project, as well as my mentor, Andrea. And I also want to thank the risk organizers, Rachel, Morgan, and John, for just organizing everything in this event and helping us through every step in this process. I really do appreciate it. And finally, all the fellow risk students that made this experience and summer really fun. Thank you.